Okay guys, here is your first example. It's a really easy one with the with a cubic. So this is a nice place to approach because we kind of already should be able to expect what this is going to do. We know that a cubic makes this general shape, and again, I've got the world's worst stylus, my good ones at school, and I'm not driving in the snow to it. So we know generally the cubic should look like that. So we're just going to think about this. We know that the domain should be negative infinity to positive infinity. And my range should also be negative infinity to positive infinity by the shape of that cubic. We know that we should maybe have like 1 point of inflection and then 2 possible changes in concavity. That's kind of what we're expecting. Or 2 types of concavity, I should say, and then maybe increasing to decreasing to increasing again. So maybe 2 changes in the types of increase and decrease. And that looks like a mess. I'm going to stop right there with that. However, we know that there are no asymptotes of any kind. What we don't know is necessarily, well, we sure know. We know that it should be going to negative infinity and positive infinity in the end. Those would be the end behaviors. But let's go ahead and write that out just for practice sake. The limit of y, as x is going to go to infinity. So let's take a look at this. That goes to infinity, that goes to infinity. It doesn't really matter what this is doing because it's smaller, kind of based on the lecture we did last time. So it's just infinity. So I know that if it goes to positive infinity, it's going to go to positive infinity. And then if limit x goes to negative infinity, y equals, so if this goes to negative infinity, that x cubed will go to negative infinity because a negative times a negative is a positive times another negative would go down to negative infinity. So those are the limit behaviors. So those become the end points for my graph. Okay? So I have now conceptualized this completely. I'm ready to do the work in terms of finding the critical points and the POIs. So what I'm going to do is I'm going to pause the video now and I'm going to set up a table on another slide because I'm going to do it on my notebook. And I'll let you, this is a good time to pause the video and find it out on your own. Okay, so here is the work I did in terms of the first and second derivative, and I found the critical points and the points of inflection. Notice that I haven't done anything else. So now I'm going to go ahead and set up the structure of the table. So it's a good place to pause. Okay, so here is the table as promised. Notice that I have very carefully articulated some things on here. I articulated the points on the intervals that I want to consider, so the easy ones. I also articulated which ones were POI and which one was a CP. I included the end behavior on F. And another thing I did that's I think is going to help you guys a little bit further is, for example, for a CP. I know at a CP my F prime is 0. That's the definition of a CP. But it's not a POI, so therefore this shouldn't change. So I drew a circle around it to let myself know that if this is positive over here, this should be positive over here, and vice versa. I shouldn't have a positive-negative relationship here. These should be consistent. And if you feel confident in your values, you wouldn't have to solve it twice. You could just say if this is positive, then this must be positive, and this must be positive. If this is positive, this must be positive. This must be positive, because the first derivative shouldn't change at the POI. That's only the second derivative. So what I'm going to do is I'm going to flip to the next screen, and I'm going to fill this table out so you can check your work, and then we'll talk about graph sketching. So this is my complete table. Notice that I put this row down here, this shape. I'm wondering if I can highlight this. This shape right here. Right here is what I'm going to use to graph my graph at this point. And so that's kind of the extra row that's the key here. Sure enough, on around my CP, my concavity didn't change. Around my CP, my concavity didn't change. Around my point of inflection, my decreasing didn't change. And now I also have some point values that I can use to graph those things and just get a general perspective of what this graph looks like. So the last piece I'm going to graph live on here because I want you to see how I graph it. And again, I'm doing my very best with a really terrible syllabus. So I'm going to shrink this way down, like so. And then I'm going to input a graph. Okay, so I have this new graphing point. I'm going to get a pencil and do my level best to actually make this work. So the first thing I'm going to do is I'm going to graph the critical points and the POIs because I have an X and a Y value. So it looks like -1, 7, so right about there, and again, world's worst stylist. I'm going to make a go of it. 0, 5, right there, and 1, 3. Okay. I also know that I have an endpoint. On the negative infinity side, it's going to go to negative infinity. And on the positive side, it's going to go to positive infinity. So I draw something like that. And then I use the shapes. So from negative infinity to -1, it's supposed to, I've got that visual, it looks like this. So then I just have to transfer that to the graph, like so. That should be a max, and then the value after that swoops down to that right. So I'm going to go down, and then I'm supposed to have a point of inflection, so I want to deal with that. So I have that point of inflection there, draw it in black so it's clear. It kind of should do something like that, where it goes concave from concave down to concave up. And then I'm going to go back up to the positive infinity, and I get my general shape of the cube.